I got a new way to make my computers work and whatnot, and it should be easier for me to show you things both with your remote and in class. I have some new projectors coming, and I've been transforming the room this weekend. I'm gonna like how it is whenever we get back. All right, in the materials section, you see that things are reorganized a little bit. Oops, hold on one second. Cancel. All right, so in the materials section of the course, there's a separate folder for where it says Unit 7 Stoichiometry, Unit 8 Gas Laws. In the Unit 8 folder, you'll find both what we did at the end of the week last week, where it says Gas Laws, and this Gas Law Worksheet 1. There's a couple problems on the back of that we didn't go over, and I want to go over those with you today. And then there's a one here that says week of 329 and 330. So that's really only 2 days. Hold on, let me fix something here. There's, I'm just going to hit mute. There's like 6 or 7 people have mics hot. Okay, that's a little bit better. I'm just hearing all that like background noise and stuff. So in the thing for this week, there's a schedule for the week, which is just today and tomorrow. There's no school, Wednesday and on. So today we'll go over stuff about Dalton's laws and Graham's law. And there's in the folder a thing about Dalton's and Graham's law. And there are some extra problems on there related to the combined gas law, Boyle's law, Charles' law that you can practice for tomorrow. Tomorrow we'll go over those problems, and there'll be a quick check about gas laws. So let me show you what I mean. So we're in the folder. You'll see here it says Dalton, Law of Dalton and Graham, student notes outline. That I would have passed out for you to be able to like fill in as we go, but so you can either look at it that way, or the one that says complete notes has all the stuff filled in. So that's like the complete notes for the day. This thing here that says Honors Chemistry Gas Law Worksheet with Dalton and Graham. These problems here, I'll do a couple with you at the end of the period as examples, and then those are like kind of practice for homework, and then we'll do those. We'll go over them tomorrow, and then whenever we come back from break, we're gonna do a whole bunch more work with gases. So anyway, in go back to this. There was that paper I gave you last week, and there were 3 problems on the front and then a few problems on the back. And we already went over a couple of them. I did some as examples in class. We went over some of them. But the ones that we didn't go over are the ones that are on the back where it says combined gas law. And so the combined gas law is like P1V1 over T1 is equal to P2V2 over T2, where you've got some initial and some final pressure and volume. So the way to think about it is like the 1 is some initial condition and 2 is some final condition, so that we've got some kind of gas and we know its volume and pressure and temperature, and then some change happens. Either we compress it, or it gets into a cool area, or we allow the volume to increase, something like that. And as a result, there can be changes in 1 or 2 or 3 other things, depending upon whether or not the container is rigid, whether or not the temperature stays the same. There's all kind of different sorts of situations. But in this first problem, there's some kind of volume, and this thing has a volume of 106.0 liters, and the temperature is 45 degrees Celsius. And I told you that these temperatures cannot be in Celsius in the equation. You won't get the right answer. They must be absolute temperatures in Kelvin. So you want to go ahead and just add 273. And it's smart to add that, right away. That way you kind of catch it immediately. That's like 318 Kelvin. And the pressure is 740 millimeters of mercury. It doesn't matter what the pressure unit is. The pressure could be in atmospheres, millimeters of mercury, kilopascal, torr. This is 1 atmosphere is the same as 760 millimeters of mercury, 101.3 kilopascal. The unit, the torr, is the same as millimeters of mercury. Torr is for named in honor of Evangelista Torricelli, the person who invented the barometer. So anyway, we're going to go to a different temperature and a different pressure. So the temperature goes down, and as a result of the temperature going down, you should expect the volume to decrease. Whenever a gas is cooled, the particles move slower. They move a shorter distance in between collisions. The amount of energy in each collision is less. So you can expect the volume to be less because the temperature goes down. And also, the pressure is going to go up. So a greater pressure acting on the gas is going to squeeze the gas to be a smaller volume. So you can expect that the volume is going to be less. And the volume decreases for two reasons. It decreases because the temperature drops and because the pressure rises. Now, it's possible that the volume could stay the same where the pressure goes down and the temperature goes down and the pressure also goes down. But in this case, because you have both factors, both a decrease in temperature and an increase in pressure, you know right away you can expect the volume to be smaller. So this new temperature, T2, 20 degrees Celsius, add 273 to that, you get 293 Kelvin. And this new pressure, P2, 780 millimeters of mercury. Anyway, what we're trying to figure out is what the new volume is. How big is V2? So just some simple algebra, V2 comes out to be equal to P1 V1 T2 over P2 T1. And you got to stick all those numbers in. So the starting pressure, 740 millimeters mercury. The initial volume was 106 liters. The final temperature is 293 Kelvin. The final pressure is 780. And the starting temperature was 318. So arithmetically, this volume, 106 liters, is some starting volume, and it will reduce by some amount that's equal to the ratio of the pressures. 740 divided by 780 is less than 1, and it will also decrease because of the ratio in temperatures. 293 is less than 318, so the ratio of 293 to 318 is also less than 1. So 740 times 106 times 293 divided by 780 and divided by 318, 92, back to this color, 92 point, looks like we have three significant figures, 92.7 liters. So it's correct to predict that the volume decreases, both because the pressure increases and because the temperature goes down. So that's what you ought to get for number 4. And then, and these are all recorded. This recording will be on my YouTube, and it'll be posted on our plan for the week a little bit later on. I can do it pretty soon. So anyway, we got 10 liters of oxygen. It's heated. What's the new volume if the pressure is also increased? So this is some kind of a volume. Volume is 10 liters, and it's at STP. So STP, you know, stands for standard temperature and pressure. Standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. But we're going to look ahead and see that the pressure is going to increase to this 1520 millimeters of mercury. So that's the same as 101.3 millimeters of mercury. So it's smart for us to use a temperature that's the same as 0 Celsius, which is 273 Kelvin, and a starting pressure whose pressure unit matches the pressure unit that's mentioned in the problem. So the smartest thing to do is to use 101.3 millimeters of mercury. The pressure unit can be anything you want, but the pressure units in the problem must match. What I mean by that is when you start with the ideal gas law and you're like P1 V1 over T1 is equal to P2 V2 over T2, the pressure could be anything, but if you have two pressures, those pressures must have the same units. If this pressure is in millimeters of mercury, that's P2. This other pressure must also be in millimeters of mercury. They could both be in atmospheres. They could both be in millimeters of mercury. They could both be in torr, but they can't be different than each other. Temperatures must be in Kelvin. So anyway, what's the new volume if the pressure is also increased to 1520? Well, we're going to go to a higher temperature too. So T2, 512 degrees C. You add 273 to that. That's going to be 785 Kelvin. and this a new pressure, P2, 15, 20 millimeters of mercury. And we're looking for what's the new volume. So that's V2. V2 is P1 V1 T2 over P2 T1. You just algebraically solve for V2 by multiplying both sides by T2 and dividing both sides by P2. So it's the starting pressure, 101.3 millimeters of mercury, the starting volume, 10 liters, the final temperature in Kelvin, 785 Kelvin, the final pressure, 1520 millimeters of mercury, and the starting temperature, 273 Kelvin. Now, the volume is not necessarily easy to know whether it's larger or smaller as a result of this change, because the pressure increases, and as a result of the pressure increasing, we should expect the volume to go down. But at the same time, the temperature goes up, and as a result of the temperature going up, the volume should go up. So, but it looks to me like this pressure increases about 15 times, but the temperature only increases about 3 times. So it might be about 5 times bigger than 10, something like that. That's just kind of just a quick estimate. So let's see, 1.91, 1.92 liters. So this temperature is only 3 times larger, but the pressure increases to 15 times. So that's a ratio of 5 to 1. Dividing 10 by 5 gets you about 2, and 1.92 is pretty close to 2. So my estimate was pretty good. 1.92 liters. Now, how do you know the volume is in liters and not milliliters or cubic meters or gallons or some other kind of volume? Well, whatever unit the volume was, that's what unit this is going to be. So the pressure units must be the same, millimeters of mercury, millimeters of mercury. The temperatures must always be in Kelvin, Kelvin and Kelvin. And then these volumes will be the same units, 10 liters and 1.92 liters. So 1.92 liters is pretty good. And then number 6, so we heat up a gas and the volume increases because we're going to move a piston in a cylinder. So how this goes is you have a piston which is inside of a cylinder, and this temperature to start out is 263 Kelvin, and the volume increases from 24 liters. So this initial volume is 24 liters, and the original pressure is 1 atmosphere. The change that happens is that we move the piston up inside the cylinder. So if the piston moves up, that makes the volume larger. So the new volume is 35 liters, and the temperature goes up to 298 Kelvin. So how you can get an increase in temperature and an increase in volume is by applying heat to the gas, or it could be a combustion reaction where the number of moles of gas don't change, but those don't really exist. So you're trying to figure out the final pressure. This one's pretty straightforward because the temperatures are already in Kelvin. So you have P1 V1 over T1 is equal to P2 V2 over T2. You're trying to find P2. So P2 is equal to P1 V1 T2 over V2 T1. Starting pressure is 1 atmosphere. So the answer, its unit is going to be in atmospheres, because that's the unit that's for pressure here is P1. V1 is 24 liters. T2 is 298 Kelvin. V2 is 35 liters. And T1 is 263 Kelvin. So let's see, 24 times 298 divided by 35 and 263. 0.777 is 3 significant figures. It comes out to be 0.777 atmospheres. So that's what P2 happens to be. All right, so that's the review of the problems from the combined gas law problems on the back of the problems from, I guess that was like Wednesday. Maybe Thursday. Wednesday or Thursday last week. Okay, there's a couple more like that to practice on the second page of the worksheet that's in the folder for today. I'll show you again at the end of class. And those are going to be pretty good practice. Let's see, right here at 9:16. Oh, we got a while. Okay, so some other gas laws. There's lots of different history about gas laws. Different people contributed different things about gases. You already know about Boyle, Charles, Gay-Lussac, Avogadro. Two other laws that come about in the early 1800s are Dalton's and Graham's law. So this picture here, the person on the left is John Dalton. He lived in London. He was an English scientist, and in 1802 published what we call Dalton's law of partial pressure. Picture on the right kind of looks like Abraham Lincoln. That's Thomas Graham. He lived in Scotland, and in 1848 published a law which we can now call Graham's law of effusion, but it's also called the law of diffusion. And effusion and diffusion have different uses, different meanings. So anyway, that's who Dalton and Graham are as you read about Dalton's law and Graham's law. All right, so a lot of the problems we've done are about gases that are pure gases. So for instance, you could have a box with maybe carbon dioxide in it as just a pure gas. The reality is most gases are actually mixtures of gases. And the best example of that is our atmosphere. The air that you breathe is not pure oxygen, not even close to pure oxygen. A lot of people are like, oh, there's oxygen in the air, and that's what air is mostly made out of. And it turns out the atmosphere is not mostly oxygen. The atmosphere is mostly nitrogen. Nitrogen gas uh, is about 79, or sometimes just people round it to 80% of the atmosphere. So the air you're breathing right now is about 80%, or about 4 and 5 molecules are nitrogen gas. There's also oxygen in the air. There's no doubt about that, but it's only about another 20% of the atmosphere, 21%. So between nitrogen and oxygen, those two gases make up the vast majority of the atmosphere. Other gases exist like carbon dioxide. There could be carbon monoxide. There are nitrous oxides, which come about as a result of combustion reaction. There's a little bit of argon. There's a little bit of xenon, a little bit of neon. Radon gas can come up into the lower levels of basements and stuff as a result of radioactive decay. But all those other gases combined are a very, very small portion. The thing is that when you have what we call air, so if this is air, the air itself has nitrogen, oxygen, carbon dioxide. Oh, another one that's not mentioned here is water, like water vapor. Uh, the as you exhale water vapor. There's um, radon. There's argon. There's all kinds of different gases. So the air itself is a mixture, and the pressure that you feel is as a result of the sum of the pressures of each of the individual gases. So Dalton's law of partial pressure is that as a result of all of the gases in the air, you get a total amount of pressure that's the sum of the pressures of the individual gases. And it turns out that the proportion of the pressures is the same as the proportion of the makeup of the gases in the air. So here, these are the different, what we call partial pressures. This is the partial pressure of nitrogen. Partial pressure of nitrogen. And this is the partial pressure of oxygen. When you add all those up, the sum of all those pressures, the symbol, the Greek letter uppercase sigma means the sum of the individual partial pressures is equal to like the total pressure or the atmospheric pressure. So this pressure of nitrogen plus oxygen plus carbon dioxide plus all the other gases for our atmosphere comes out to be about 101.3 Pascal. It also means that the atmosphere is also 79.1% nitrogen and 21.1% oxygen by composition. So if you have a gas and 50% of the pressure is from one gas and 50% of the pressure is from another gas, then those gases are actually equal in composition. There's an equal quantity of them in the gas itself, in the mixture of the total gas. And when I say gas, I don't mean gas like gasoline, gas, the phase for air. So, for instance, you could have a mixture of a gas with oxygen, nitrogen, and helium. Um, Scuba divers breathe compressed air, and scuba equipment for firefighters. That's also compressed air. It's just the regular air in the atmosphere that's compressed. But scuba divers can also breathe a mixture of helium and oxygen. It's called heliox. And that heliox mixture has a greater quantity of helium in it than the atmosphere does at all. And that's very useful for deep sea diving. So, but anyway, maybe we have some kind of gas here. This is just a simple example. And in this example, there are three different gases. There's oxygen, and the pressure from the oxygen is 20 kilopascal. There's also nitrogen. So you've got some oxygen gas, there's nitrogen gas, and then there's some helium. And each of those gases are in different proportions and different concentrations in the total sample of gas. The partial pressure of oxygen is 20, nitrogen is 46.7, and helium is 26.7. The total pressure is just the sum of those. So 20 kilopascal plus 46.7 kilopascal plus 26.7 kilopascal. So let's see, we got 66.7 and 26.7 comes out to be 93.4 kilopascal. A way to think about this gas too is if that gas mix, and it's all blended up, of course, but you'd have a certain proportion of it would be oxygen. So if this is the proportion that's oxygen, that's 20%. Well, not 20%. I gotta go back because this is 93.4. The percent that's oxygen is equal to the partial pressure, 20 kilopascal, divided by the total pressure, 93.4. So 20 divided by 93.4 is 21.4%. So this is 21.4% oxygen. The helium is a little bit more helium than oxygen. So here's where there's some helium. And that's 26.7 kilopascal. If you take 26.7 divided by 93.4, you get you 28.6%. And then the rest of it is nitrogen. So the nitrogen happens to be 46.7. If you take 46.7 divided by 93.4, you get, well, that's 50%. 50% nitrogen. So of the total pressure of the gas, it looks like exactly half the pressure comes from nitrogen, and then 28.6% from helium and 21.4% for oxygen. Those percents compositions for each of the gases is the partial pressure for the gas divided by the total pressure. For now, all you got to really worry about is how the total pressure comes about as a result of the individual gases. So in the worksheet I'll show you, we'll do one example that's like that. It's just so simple that the total pressure is just the sum of the pressures of the individual gases. Or if you happen to know the total pressure and the pressures of two of the others, you can calculate how much pressure must be about for the unknown. All right, so we'll do some examples in just a minute. But Graham's law deals with another concept, and that's that whenever you have gases in a sample, so long as the densities are about the same, the gases will be evenly mixed among each other. So, for instance, if you're in a room, it's not like all the oxygen gas is just over here in one corner and the rest of the air is nitrogen. That would be terrible because the only breathable air would be down here where the oxygen is because you need oxygen to breathe. And the air over here would suffocate you. So we don't find that to be true. It isn't like, it's never the case that when you're walking around in your daily life, you get to a place in the atmosphere and you're like, oh man, there's not much oxygen here. I got to move over a little bit. That just doesn't happen. The oxygen is pretty well, um, pretty well distributed all throughout in a gas. So there's this general law of diffusion. Diffusion is the general spreading of gas molecules throughout a container until they're equally distributed. So instead of the nitrogen all being clumped here in one corner and the rest of the nitrogen being in the room, instead, you have nitrogen molecules and you have oxygen molecules and they're all pretty well evenly spread out. There's more nitrogens than oxygens in the air, but it's not as if the oxygens only exist in one particular or certain place. Instead, the particles are all pretty well evenly distributed. And that comes about because these individual particles themselves are in motion. They're free to move around relative to each other, and they're all going in different kinds of directions. They make their way around the room, so they're fairly evenly mixed. Now, in a gas where they can vary in density, it can be a totally different story. So, for instance, if you have a high density gas, that high density gas can be very close to the ground, and the relatively low density gas will exist above it. So you might have learned, like, in elementary school about fire safety, that if you're in a burning building, you shouldn't try to walk, through the building if there's smoke in a room with your head up in the smoke because you can't see, but you should get down close to the ground and maybe crawl. But you have to be very careful because as materials burn, the gases that come off them can be of very high density, and those very high density gases will always pool very close to the floor. So it's critical that you not have your face too close to the floor. And then the other example that I just mentioned about our atmosphere is for a house. You could have, like, a house with a basement, and radon gas is a product of natural radioactive decay of uranium, and that radon gas can seep into basements. And it turns out that radon gas intrusion into basements is more common in Pennsylvania than many places in the country, and companies make businesses of doing radon mitigation. Radon has a very, very high molecular weight or very high formula mass, so it actually tends to collect and pool in basements of homes. So if you have high radon levels in your home, they're usually as a result of high radon levels in the basement in the lower level. So especially if you have living spaces in the basement, it's very important to make sure that you don't have radon in the home. And radon remediation companies remove that radon usually by putting a fan in line with a pipe that can draw air from the bottom of the basement floor up through and out the exterior wall of the home. That's because the radon will, because of its high density, will tend to be in the bottom. But nitrogen and oxygen and carbon dioxide, they have relatively similar formula masses. So we don't find that just because oxygen has a higher formula mass than nitrogen, that oxygen is lower in the floor in a room than nitrogen. The speed of the particles is sufficient to get them to move around. The other issue is about how gases can move through pores and small openings. So that principle is the principle of effusion. And the only real difference between effusion and diffusion, besides the small difference in spelling, is, well, there's a couple different issues. One of them could be you could have a surface that's um, through like a hole. The hole in the container could be pores, so it could be like a membrane that has small holes in it, and those holes can allow gas to travel through. So you could have a particle of gas and it's traveling and it's able to get through the holes of the pore in the wall. You might know that, like, if you have a helium balloon that's a rubber latex helium balloon, it'll be really full right away, but if you wait over a couple days, it'll kind of deflate. That's because the walls of the balloon are not, although they seem solid, they're not totally solid. There's pores in the balloon that the low density gases can escape through or leave. Or similarly, like if you have a door to a room, so like here, I'll draw it like this. So here's like a doorway, and the door is like cracked. Get it? So it's like this. Yeah. So you could have the door like cracked in a doorway. There's an opening where the gas can transfer from one space to the other. Um, the the general principle is that both with effusion and diffusion, you have the motion of particles. Those particles are able to move, and they have a velocity. Now, if this opening is very small, uh, the number of particles that can travel through the per amount of time is small. If the opening is large, more particles can get through. But we also find that if you have gases of dissimilar masses, that the smaller mass particles are moving faster and effuse more quickly than the higher mass particles. So here's a way to know what's going on. In a sample of a gas, maybe you have oxygen and helium, and they're at the same temperature, and maybe you have equal amounts of each. So you have 50% of it is oxygen and 50% is helium in a sample of a gas. Oxygen, O2, has a mass of 32 grams per mole. Helium has a much lower formula mass, 4 grams per mole. And it turns out that as a result of their differences in masses, well, they're going to have the same amount of energy. The oxygen molecule is relatively large in size and it'll have a relatively low velocity, if this arrow represents the speed. The helium, though, is a much smaller particle, and it has a much higher speed because it turns out that those particles will have the same, what we call kinetic energy at any temperature. So, if you compare oxygen and helium, a high mass gas and a low mass gas, the higher mass gas is going to be moving slower and the helium is going to be moving faster. So this is fast and then this is slow. So here we've got an example. I've got two gases, oxygen and some other gas. So if I've got some oxygen, here's O2, and it has a speed of about 4 centimeters per second. And there's some other gas with a speed of 8 centimeters per second. Well, if it's got a speed of 8 centimeters per second, it must be smaller and it must be moving faster. And it turns out, well, is the other gas CO2 or is it helium? Well, I already figured it out, but oxygen has a mass of about 32 grams per mole. And CO2, if you want to figure out its mass, one carbon and two oxygens, carbon has a mass of about 12. Oxygens each have a mass of about 16. So that's about 44 grams per mole. Carbon dioxide has a much higher mass than oxygen does, so it's not reasonable for the other gas to be carbon dioxide, but it is reasonable for that gas to be helium. So the higher you could say this, the speed for the CO2 is going to have to be less than the 4 centimeters per second because it has a higher mass than the oxygen does. And in order for the carbon dioxide to have the same kinetic energy as oxygen, it can have a lower speed. And then it turns out that if you have, so in comparing oxygen, helium, and carbon dioxide, if you have a sample of a gas in a container, and let's say that we begin by segregating the gases. So let's say that I've got we'll do the helium like here, and then I've got some oxygen here, and then there's some CO2 up here. So the gases are segregated so that they're like in different sections. It turns out that all the particles in that gas, given enough time, will end up mixing up. They will diffuse throughout each other so that there's an equal amount of concentration. But the gases do it at a different rate. Because the helium has a much higher speed, you can expect that that helium gas will diffuse through the container at a much higher rate. In other words, at any moment in time, an individual helium molecule, helium atom, could travel at a very high speed. They're also relatively small, they're uncharged, so the helium atom you can expect to travel a large distance in some amount of time. The CO2 molecule, on the other hand, has a much lower speed, and you can expect that the carbon dioxide will take more time to spread throughout the container than the helium does. But nonetheless, the total pressure of the gas is equal to the pressure of the carbon dioxide, the oxygen, and the helium all added up. So anyway, I'll go back to this thing, show desktop. Here we go. In the folder for this week. So this is in Unit 8, week of 329 and 330. There's this paper here that says honors chemistry gas law with Dalton and Graham. And these are problems that I want you to do and think about as practice for tomorrow. We'll go over them tomorrow, and that'll be the last thing before our break. In these problems here, there's a couple different ones that are about, partial pressure and total pressure, and some other concepts about effusion and diffusion. And the most important thing to do all the time is to figure out what the formula masses of the gases are, and compare those masses to figure out, which of the two would tend to go slower or faster. The lower mass gas is going to be a faster gas than the higher mass gas. But here we'll just do a couple as practice. So um, some things to practice include like unit conversions for gases, some gas law problems, some concepts about Dalton's partial pressure, and Graham's law of effusion and diffusion. One thing you got to practice here is about unit conversions. So here I've got some kind of pressure in millimeters of mercury. We want to convert it into kilopascal. That's what kPa is in kilopascal. You know that you can convert by using a conversion factor where the numerator and denominator are equal in value, and these pressures are all equal pressure units. 1 atmosphere is the same as 760 millimeters of mercury. It's about 101.3 kilopascal. So if we want to convert from millimeters of mercury to kilopascal, millimeters of mercury's got to go in the denominator, kilopascal has to go in the numerator. And the numerator and denominator of a conversion factor always have to be equal in value. So what I'm doing is I'm looking for values that I can put in the numerator and denominator so that the numerator and denominator are equal to each other. And up here, 760 millimeters of mercury is the same as 101.3 kilopascal. So then on your calculator, if you go 698 times 101.3 divided by 760, let's see, 101.3 divided by 760, that's like 93. We have three significant figures. So 93.0 kilopascal. You can do 1B, changing that pressure in atmospheres into kilopascal. The other example I wanted to do before I let you go is this one about I got a couple minutes left. You got a balloon, it's filled with some different gases, helium, oxygen, and carbon dioxide. There's a total pressure that comes about as a result of the three different gases. The total pressure is 105.5 kilopascal. And the gases that compose this mix include oxygen. So oxygen has a pressure of 20 kilopascal. CO2 has a pressure of 0.8 atmospheres. Now, you can't have a unit of atmosphere mixed with a unit of kilopascal. So this unit of this pressure in atmospheres, we got to convert that into kilopascal first. So 0.080 or 0.800 atmospheres. 1 atmosphere is the same as 101.3 kilopascal. So if you take 0.8 times 101.3, 81, I'll leave extra significant figures here, but we'll round it to 3 at the end, 81.04 kilopascal. So I have a pressure of, let's see, CO2, that's 81.04 kilopascal. And there's some other gas, some helium, and we want to know what is the pressure of helium. So the idea is that the total pressure of the gas comes about as a result of pressure from helium, pressure from oxygen, and pressure from carbon dioxide. And the sum of the pressures of helium, oxygen, and carbon dioxide are equal to 105.5. So if I subtract 20 and 81.04 from 105.5, that'll tell you how much pressure must be from the helium. So if I take the total pressure and subtract the partial pressures of the other two, 81.04, I'll get some kind of value that'll represent the amount of pressure that comes about from the helium. 105.5, well, minus 20 minus 81.04, 4.4. We only are good to the tenths place. So let's see, 81.04, 4.5. So the pressure from the helium must have been 4.5 kilopascal. That way, 4.5 plus 20 plus 81.04, really 81.0, come out to equal 105.5. The sum of the pressures is equal to the total amount of pressure. So anyway, those are just a couple examples. So I did 1A and number 1. So in the folder for this week, there's the uh, worksheet with Dalton and Graham's law. I did 1A for you, and then number 2. You should have no trouble doing 1B is like 1A, and number 3 is like number 2. And then there's some conceptual questions, 4, 5, and 6 toward the end. So anyway, that's what I have for you for today. It's kind of good that we did the mini lab on Friday because we weren't able to do labs today or tomorrow, that's for sure. So tomorrow we'll go over those problems. I'll tell you some other stuff about gases, and then that'll be it. And some of you might have to send a message about uh, making sure you complete the second part of the test because there's 2 people who didn't. I forget who, so I gotta check up on that. So make sure I get those all graded and put in the grade book and whatnot, and then that'll wrap up this marking period. If you have questions, you can put them in the chat. Turn on your mic and ask them now. Otherwise, I'll see you tomorrow.